Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for your upcoming test. So this video is for the advanced test, so you might want to check with your teacher if you're in a mainstream class how much of these topics apply to you. So the blue topics are statistics, then we'll go through the yellow, which is probability, and the black, which is indices and surds. So let's start with grouped frequency tables. So we start with statistics, and that involves scores, sets of data. Sometimes what will happen is we will look at data where there are heaps of possible scores. So for example, let's say I gave a test to my class and they could score anywhere between 0 and 60. Well, of course, I wouldn't want to write out how many people scored 0, how many people scored 1, how many people scored 2, all the way up to 60. That would take too long. So when there are lots of possible scores, what I might do is group the data. So what I've done here is I've put the data into groups of 10. So this is how you read it. So this first one is all the people who scored more than 0 but less than 10. So we include 0 in this group, but not the people who scored 10. The people who scored 10 are included in this group. This is all the people that scored either 10 or more but less than 20. And all the people between 20 and 30 in this group, but we include the people who scored 20, not the people who scored 30, and so on. So we do this so each group is the same size. It has a class width of 10. So we have a column for the scores in a grouped frequency table, and then we have a column for frequency. So frequency is just how many times the score occurred. So this is saying 2 people scored less than 10. 3 people scored 10 or more but less than 20. 5 people scored 20 or more but less than 30, and so on. So what we need to be able to do from this group frequency table is estimate the mean and the median. Now, we can't calculate exactly what the mean and median are because we don't know the individual scores. So, for example, we know 2 people scored less than 10 marks in this test. We don't know whether they scored 0 or 1 or 9. So because we don't know what these 2 people actually scored, we can't calculate the mean and median. But this is a little trick. It's a bit of a cheat, if you like, that helps us estimate the mean and median. What we do is we pretend that these 2 people scored halfway between the 2 endpoints of this group. So that probably sounds a bit weird. What we're going to do is we're going to create a column that has the midpoint of each group. So the midpoint of the group 0 to 10 is equal to 5. So I'll just put a 5 there. The midpoint of the next group, halfway between 10 and 20 is 15. Halfway between 20 and 30 is 25, and so on. So what we're going to do to estimate the mean and median, we're kind of going to pretend that these 2 people both scored 5, that these 3 people all scored 15. We're doing this because, like, say in this group, it's like these 5 people on average scored 25. So let's first calculate, or estimate rather, the mean. So you should know by now the mean is the sum of the scores. So that symbol means sum of x. X is the score. It's the sum of the scores over n, which is how many scores. So we can easily calculate how many scores by adding up the frequency column. So this symbol here means sum of frequency column. So if I add up all of these numbers, I get 32. That's n. The number of scores here is 32. Now I need to estimate the sum of the scores. So what I need to do is create another column. So in this column, what I'm going to do is I'm going to multiply each score by how many times it occurred. That's just an easy way to add up all the scores. So if I call the midpoint m, in this column, I'm going to multiply the frequency, how many times the score occurred, by the midpoint. So what goes in this column? It's just 2 times 5, 3 times 15, 5 times 25, and so on. So after creating this column, I'm going to add them all up. So the sum of the FM column, if I add up all those numbers, gives me 1120. What this actually is, this is an estimate of the sum of all the scores. My estimate is that all of the scores will add up to 1120. So in this case, I'm going to estimate the mean as just 1120 divided by 32, which gives me 35. So that's how you estimate the mean. So again, you'll be given a column of scores, a column of frequency. You calculate the midpoint, create a column of midpoints. Then in the next column, you times each midpoint by its frequency. Adding up all these gives us the sum of all the scores, or an estimate of the sum of all the scores. Adding up the frequency column tells us how many scores there are. Sum of all the scores divided by the number of scores is an estimate for the mean. So let's look at the median. So to calculate the median when there are a lot of scores, it's helpful to use this formula n plus 1 on 2. Now, n, remember, was the total number of scores. So the sum of the frequency column, in this case, 32. So in this case, if n is 32, then n plus 1 on 2 is just 32 plus 1 on 2, which gives you 16.5. But hang on a minute, there's no way the median of this data could be 16.5 down here when there are so many scores are above it. This formula here, n plus 1 on 2, doesn't tell you what the median is. It tells you which score is the median. The point of it is to tell us, is the third score the median, or is the 10th score the median, or whatever. This is saying the 16.5th score is the median. That doesn't make any sense. What this means, because I didn't get a whole number, it means the median is halfway between the 16th and 17th score. So remember, if there are an even number of scores, there will always be two middle scores. And to find the median when there are two middle scores, you add up the two middle scores and divide by 2. So what is the 16th and 17th score of this data? Well, what we're going to do is create another column. We're digressing a little bit. And this column I'm going to call CF for cumulative frequency. So what CF column does is it tells us how many scores are less than or equal to a particular score or group. So what do I mean by that? So what we know from the frequency table is that there are 2 scores that are less than 10. So I'm going to put a 2 here. 2 scores less than 10. So now I go 2 plus 3 is equal to 5. This 5 is telling me there are 3 plus 2, there are 5 scores less than 20. So what goes here is 5 plus 5, which is 10. There are 10 scores that are less than 30. So now 10 plus 8 gives me 18. There are 18 scores less than 40, 28 scores less than 50, and 32 scores less than 60. So that's what a cumulative frequency column is. Again, number tells us how many scores are less than a particular score. In this case, there are 18 scores less than 40. So how is this going to help us determine the median? Well, here, the median is halfway between the 16th and 17th scores. So we know there are 10 scores less than 30. There are 18 scores less than 40. So what that means is the 11th, 12th, 13th, 14th, all the way up to the 18th score is in this group here. The 16th and 17th scores are both in this group here. So this is like our middle group. So because they're both in this group, I'm going to estimate the median as the midpoint of this group. So I'm also estimating that the median is 35. So I know that these calculations with grouped frequency tables, they are a pain. They take a long time. So for median, use n plus 1 on 2. That tells you which score is the middle score, and the cumulative frequency column can help you locate that score. So if it's the 16th or 17th score, you find which group that score is in, and the midpoint of that group is the median. All right, let's now move on to stem and leaf plots. So here I have 2 sets of data. So let's just say they're test scores for boys and girls. I'm going to put this in what's called a back-to-back stem and leaf plot so I can compare boys and girls. So what I'm going to do is I'm going to put boys over this side and girls over this side. So in the middle of a stem and leaf plot goes the stem. This is basically the number of tens. So the scores in these sets of data go from 60 all the way up to 100. So here I'm going to put all the scores in the 60s, 70s, 80s, 90s, and 100s. So let's put all of these boys' scores over here. So what we do is we have the lowest scores closest to the stem. So for the scores in the 60s, we have 8 and 8 for boys. So this represents a score of 68. This represents a score of 68. So for the scores in the 70s, as I said, the lowest scores go closest to the stem. So I'm going to go 4, 7, 9. For the scores in the 80s, 84, 84, 84, and 86. Then I have 92, 92, 92, 96, and 99. So that's boys done. So for girls, I'm going to do something similar. So I'm going to put 62 here. So this is the number of tens. The number I put here is just the number of units. For 75, I just put a 5 here. So remember, lowest scores closest to the stem. And I will get something that looks like this. So this is what a back-to-back stem and leaf plot looks like. The advantage it has over the group frequency table in the previous slide is that I actually know each individual score. So I can calculate the mean, median, and mode as normal. So let's say I wanted to calculate the mean for boys. I just add up all the scores and divide by how many there are. So the mean would be adding up all the scores. I get 1175. There are 14 scores in total. So to one decimal place, the mean of boys is about 83.9. So let's look at the median. So I'm going to calculate the median in the usual way. So when you have the data arranged in a stem and leaf plot, the useful thing is that it's already in order from smallest to largest. So this is how I can use stem and leaf plots to calculate the median. I want to find the middle score. So I'm just going to cross off the lowest score and the highest score. Then I'm going to cross off second highest and second lowest. And what I'm going to do is keep crossing off the scores in order, and eventually I will meet in the middle. So you can see here the two middle scores are both not 4 but 84. So you can see, compared to these scores, there are 6 scores lower than or equal to 84, and there are 6 scores more than or equal to 84. So the median here is 84. Remember, when there is an even number of scores, there are 2 middle scores. So the median is 84. So I could do the same for girls. Cross them out in order and keep going like that. If I keep crossing them out for girls, though, it turns out I have only 1 middle score. So the median here is 85. So once again, we can see that there are 5 scores below 85 and 5 scores above. The same number of scores above the median as below the median. So for the data for girls, there are only 11 scores. There are an odd number of scores, which is why there was only 1 middle score. Odd number of scores, 1 middle score. Even number of scores, 2 middle scores. And if you have 2 middle scores, you average them to find the median. So the mode of each data, that's the easiest to calculate. The mode is just the most common score. So it's not which score is repeated. So here for the boys, we can see 68 occurred twice, but it's not the mode because 84 and 92 occurred the most. They both occurred 3 times. So this data actually has 2 modes, 2 most common scores. If it has 2 modes, we call it bimodal. For the data for girls, on the other hand, there was only 1 score that occurred the most. 81 was the only score that occurred twice. So the mode for girls is 81. We say it is unimodal. It has only 1 mode. Bimodal has 2 modes. Unimodal has 1 mode. All right, the last thing we need to do with statistics is look at skewness. So I'm going to get rid of the mean, median, mode calculations. Pause and copy them down if you need. So when we're describing the skewness of data, it can be positively skewed, negatively skewed, or symmetrical. It's all about whether there is a higher frequency of scores closer to the maximum, minimum, or middle. It sort of goes in the opposite way that you'd expect, however. People would expect positively skewed, there'd be more high scores, and they'd cluster towards the maximum, but it's the opposite. Positively skewed means there are more low scores, more scores clustered towards the minimum, and negatively skewed means there are more high scores or scores clustered towards the maximum. So for boys, we can see there's a higher frequency of scores at the top, closest to the maximum. So for boys, we would say they're negatively skewed. So for girls, we can see the highest frequency of scores occurs in the middle. So we would say for girls, that data is symmetrical. So let's look at what it would look like if I were to draw a histogram. So starting for boys, what would happen is there's only a few scores in the 60s, there's one more 3 in the 70s, there's 4 in the 80s, and 5 in the 90s. So what would happen for boys is as the scores are getting greater, the frequency is increasing. Remember, in a histogram, you always have frequency as the vertical axis. Higher bar means higher frequency. So there'd be more scores in the 90s, more scores closer to the maximum. For girls, what's happening is there was just one score in the 60s, 2 in the 70s, and then there were heaps. There were 5 in the 80s, back to 2 in the 90s, and 1 score of 100. So you can see that the shape of this is symmetrical. The highest frequency, the highest bar, occurs in the middle. All right, that's all for statistics. Let's move on to probability. So remember that probability is the assigning to random events a number to indicate how likely it is to occur. So in probability, we look at random events, events whose outcome is at least partly due to chance. So we give these random events a number. The number has to be between 0 and 1. So if the number we give to the event is close to 1, that means it's likely to happen. If the number we give to an event is closer to 0, it means it's unlikely to occur. So probability always has to be between 0 and 1. If I say, what is the probability something happens, you can't give me the answer 2 or -3. You must give me a number between 0 and 1. So just as percentages add to 100%, probabilities add to 1. So like if you had a test and you answered 80% of questions correctly, that means 20% of your answers were incorrect. So the same is true in this question. So the probability my team wins is 0.8. So I'm just going to write it like this. So this means probability of winning is 0.8. That means the probability that my team doesn't win is equal to 0.2. So this dash here means not. So probability win is 0.8, probability not winning is 0.2. So what does this actually mean? When we give a probability to an event, we're finding the proportion or fraction of times we expect something to happen. So 0.8 is the same as 4 over 5, and 0.2 is the same as 1 over 5. So if the probability that my team wins is 4 over 5, that's saying if we play heaps of games, we expect to win 4 in every 5 games. We expect to win 4/5 of the time, so we expect that we won't win 1/5 of the time. So if my team were to play 35 matches, I would expect that we do not win 1/5 of the time. Now, of means time. So we'd expect that we would not win 1/5 of 35, which is 7 times. So again, probability is just the fraction of times we expect something to occur. So calculating these probabilities can be difficult, and that's why we need a bunch of rules and tools to help us. So let's now look at the or and rules for probability. So we're going to look at A and B and A or B. So if we have two sets A here and B here, where they cross over, we write like this, and we read it as A and B. So A and B is just the middle section of a Venn diagram. A or B means we're in A or B or both. It's everything inside the circle. We write it like this, and this means A or B. So let's come up with a rule to calculate A or B. So if I want to find the probability I'm either in A or B, that either A happens or B happens, well, what I can do is find the probability that A happens, add up everything in A, and add up everything in B. So the probability of A or B, I can just add together the two probabilities. The problem is if I add A and add B, this middle region, A and B, has been double counted twice. I counted it both times. So because this green region here has been counted twice, I need to subtract it. So it's only counted once. And that's how I come up with the OR rule for probability. So the OR rule says the probability that A or B happens is probability A plus probability of B minus the probability they both happen. So know this formula and also make sure you understand the difference between this symbol, which means OR, and this symbol, which means AND. So let's look at how we would use this in a question. So I pick a card from a normal deck of 52. What's the probability the card is a heart or an ace? So I'm finding the probability of heart or ace. And so my rule up here is telling me the probability that it's a heart or an ace. I find the probability it's a heart, add the probability that it's an ace, and then I subtract the probability that the card is both. So if I have a normal deck of cards, the probability of getting a heart is 1/4. There are 4 suits: hearts, diamonds, spades, and clubs. Hearts is one of them. The probability of getting an ace is 4/52. There are 4 aces out of 52 in the deck. So what's the probability of both a heart and an ace? Well, there's one card in the deck that is both a heart and an ace. That's the ace of hearts. So the probability of both is 1/52. So probability heart plus probability of an ace minus the probability of both. So you can put that straight on your calculator. You get 16/52 or 4/13, and we're done. So another definition we need to know is that of mutually exclusive. So 2 events are mutually exclusive if they can't both happen at the same time. So a mathematical way to say that 2 events A and B are mutually exclusive is that the probability that both of them happen is 0. So example, you get an A in maths, you get a B in maths. They are mutually exclusive. You can't get an A and a B in maths at the same time. That doesn't make any sense. So if 2 events are mutually exclusive, when we're using this rule, we don't need to worry about probability of A and B because it's 0. So let's look at an example. So I pick a card from a normal deck of 52. What's the probability the card is a 4 or a 5? So the event the card is a 4, the event the card is a 5, they are mutually exclusive. You cannot have a card that is 4 and also 5. You can't have both of these happen at the same time. In the previous example, heart and ace are not mutually exclusive. You can pick a card that's a heart and also an ace, but you can't pick a card that's both a 4 and a 5. So here the events are mutually exclusive, here they're not. So if I want to find the probability the card is a 4 or a 5, well, I can use this rule up here. So I have the probability that it's a 4 or a 5, so it will just be the sum of their probabilities. I don't need to subtract the probability that I pick a card that's both a 4 and a 5 because it's 0. You can't have that. So the probability I pick a card that is a 4 or a 5. Well, there are 4 4s out of 52 in the deck. There are 4 5s out of 52 in the deck. So the required probability is 8/52 or 2/13. And then we're done. So that's the OR rule. Let's now look at the AND rule for probabilities. So the OR rule tells us how to calculate the probability of A or B. The probability A happens, or B happens, or both happens. Here, we're looking at a rule for AND. We're looking for probability of A and B, the probability both of them happen. Now, this rule that we're going to use only works if the 2 events are independent. So 2 events are independent if the outcome of one does not affect the chances of another. For example, let's say I toss 2 coins. The outcome of each coin is independent. What you get on the first coin doesn't affect what you get on the second coin. So just make sure you understand the difference between independent and mutually exclusive. People always mix them up. Mutually exclusive is when 2 events can't both happen at the same time. Independent, they can both happen at the same time. One of them, though, does not affect the chances of the other. So if two events are independent, the probability they both happen is just the product of the probabilities. So a crude way to think about this is when it's an or question, like we had on the previous slide, you add probabilities, and when it's an and question, you multiply the probabilities. This rule only works if they're independent. So let's look at an example. We're actually going to use the and rule and the or rule in this one. So let's say I roll 2 dice. What's the probability that their sum is 10? So let's think of how this could happen. So I could get a 6 and then a 4, or I could get a 4 and then a 6, or I could get a 5 and then another 5. So what I'm really saying here, the probability that the sum is 10 is the probability I either get a 6 and a 4, or a 4 and a 6, or a 5 and a 5. So these three events are mutually exclusive. I can't get a 6 and a 4 and also get a 5 and then a 5. I can't get a 6 first and also get a 4 first. That doesn't make any sense. So because they're mutually exclusive, what I can do is add up their respective probabilities. So that's just the oral for mutually exclusive events. I don't need to subtract the probability that they both happen because I can't have this happen and this happen at the same time. They're all mutually exclusive. So you're probably thinking, what does this have to do with the and probability? Well, each of these is an and thing. The probability I get a 6 and a 4 that both of these happen, a 6 on the first go and a 4 on the second go. The probability I get a 6 on the first go is 1 over 6. The probability I get a 4 on the second go is 1 over 6. The probability they both happen, I just times together. It's the same for this. The probability I get a 4 on the first go, the probability I get a 6 on the second go, the probability they both happen, I just multiply them together. Same for 5 and then a 5. The probability I get a 5 on the first go, 5 on the second go, so the probability that they both happen, I multiply their probabilities. So I just add up these probabilities and that will give me my answer. So it's 1 over 36 plus 1 over 36 plus 1 over 36. That gives 3 over 36 or 1 over 12. So please make sure you understand the difference between the and the or rule. Please make sure you understand the difference between mutually exclusive and independent events. So let's now move on to tree diagrams. So tree diagrams are just a tool to help us with probability calculations. What they do is they help us list the outcomes of multi-stage events. So a multi-stage event is one that occurs in stages, like tossing heaps of coins, rolling heaps of die, or whatever. So let's look at this question here. So bag has 3 Mars bars, 3 crunchies, 2 boosts. I'm going to pick 2 chocolates at random, one after the other without replacement. What is the probability a Mars bar's picked? This is a multi-stage event because I'm picking a chocolate and then picking a second chocolate. So the first stage is me picking the first chocolate and the second stage is me picking the second chocolate. So what I do to draw a tree diagram is at each stage I list the possible outcomes. So for the first pick, I could pick a Mars bar, a crunchie, or a boost. So that's my possibility for the first go. If I get a Mars bar the first go, I can still get a Mars bar, crunchie, or boost on the second go. Similarly for the other two. So I stop there because I'm only picking 2 chocolates. And now what I'm going to do is list all the outcomes. So to find the outcomes, I just follow the branches. So I have MM, that's getting a Mars bar both goes, so getting 2 Mars bars, or I can get a Mars bar, then a crunchie, a Mars bar, then a boost, and so on. So you can see now the tree diagram has helped us list all of the possible outcomes if I pick 2 chocolates. These are the list of outcomes. So you might think, okay, there's 9 outcomes, so each of these has probability 1/9. Unfortunately, it doesn't work like that because these outcomes are not equally likely. You're more likely to get 2 Mars bars than 2 boosts because there were more Mars bars in the bag. So what we need to do is we need to write the probabilities on the branches. So the probability of getting a Mars bar, well, there were 8 chocolates to begin with and 3 Mars bars. So that's just 3/8. Similarly, the probability of getting a Crunchie is 3/8, and of a Boost is 2/8. So that's the probability of getting each of these chocolates on the first go. What about the second go? Well, the thing is that these chocolates were picked without replacement. So that means the probability on the second pick will change. So if I got a Mars bar the first go, there are now only 2 Mars bars left out of 7 Mars bars in total. So the probability of getting a Mars bar the second go, if I got a Mars bar the first go, is 2/7. And we're going to do the same here. So if I picked a Mars bar the first go, there are still 3 Crunchies left out of 7 chocolates in total. And there are still 2 Boosts left out of 7 chocolates in total. So now, if I picked a Crunchie the first go, well, then there are still 3 Mars bars left out of 7 in total. There are 2 Crunchies left and 2 Boosts left. If I picked a Boost the first go, there are 3 Mars bars left out of 7, 3 Crunchies left out of 7, and 1 Boost left. So notice that each of these add to 1, add to 1, add to 1. All of these probabilities add to 1. Probability should always add to 1. So how do I use these numbers on the branches to calculate the probability of each of these outcomes? What I do is multiply. So the probability of getting 2 Mars bars is 3/8 times 2/7. I'm timesing because this is like the AND rule. The probability to get a Mars bar and another Mars bar, a Mars bar on the first go and the second go, I multiply these 2 probabilities together. So 3/8 times 2/7 gives me 3/28. That's the probability I get a Mars bar. So the probability I'm after is that I get a Mars bar. So let's circle the ones that are a Mars bar. Well, if I get 2 Mars bars, then I got a Mars bar. If I get this, or this, I get a Mars bar. And if this happens, I get a Mars bar. So rather than calculate the probability of all 9 events, I'm just going to calculate the probability of these ones circled that are of interest to me. So the probability of a Mars bar then a Crunchie is 9/56. It's 3/8 times 3/7. So the probability I get a Crunchie then a Mars bar is going to be the same. 3/8 times 3/7 is 9/56. So the probability I get a Mars bar then a Boost, 3/8 times 2/7, that gives me 3/28, and this one will be the same. 2/8 times 3/7 is 3/28. So the probability I get a Mars bar is the probability this or this or this or this or this happens. Now we're looking at the OR rule, so that means add. Remember, and is times or is add. Now, each of these events is mutually exclusive. You can't pick 2 Mars bars and also pick a Boost and a Mars bar. You can't have this and this happen at the same time. Because all of these events are mutually exclusive, the probability this or this or this or this or this happens is just the sum of all their probabilities. So if I add up all of these 5 numbers here, I get 36/56 or 9/14. That's my answer. The probability I get a Mars bar, adding up all these, gives me 9/14. So tree diagrams are very useful when the events occur in more than one stage. Venn diagrams are very useful when there's more than one set. So let's go look now at Venn diagrams. So let's look at this question here. Class of 28 students, 15 play soccer, 9 play AFL, and 8 play neither. So we're going to find the probability someone plays AFL and doesn't play soccer, AFL or does not play soccer, and this symbol here means given. The probability they play AFL given that they play soccer, the probability that they play soccer given AFL. So all of these calculations would be pretty hard. What we need to do is we need to find some way to organize our information. So this question is talking about students who play soccer or play AFL. There's two sets here, AFL and soccer. So when the question involves two sets, we draw up a Venn diagram like this. So each circle represents a set. S for the people who play soccer, A for the people who play AFL. So you might be thinking, hang on, 15 plus 9 plus 8 is 32. How can you have 32 people when the class only had 28? Well, we've overcounted by 4. We've counted 4 people in the AFL circle and also the soccer circle. So however many you've overcounted goes in the middle. We overcounted by 4 because there were 32 instead of 28, so 4 goes in the middle. There are 4 people who play both. So 15 people play soccer. We've already got 4 in the soccer circle, so we need 11 more in the soccer circle. Similarly, we need 9 in the AFL circle. We've already got 4, so then we need another 5, and there are 8 who play neither. Note, 8 plus 5 plus 4 plus 11 equals 28. So the Venn diagram, and this is what a Venn diagram looks like, is just a way for us to organize our information. So let's go ahead and calculate these probabilities. So firstly, the probability of AFL and not soccer. We're looking at people in the AFL circle who do not play soccer. So in the AFL circle, these 4 play soccer, these 5 do not play soccer. So there are 5 people here who play AFL and not soccer. There are 28 people in total. So now we're looking at AFL or not soccer. So we are going to include these people here because they play AFL, these people here because they play AFL, and these people here because they do not play soccer. So 8 plus 5 plus 4 is 17. So we have 17 people play AFL or do not play soccer out of 28 in total. So these last 2 questions are a bit different. These are examples of what we know as conditional probability because we've put a condition. Here we're saying probability they play AFL given that they play soccer. We're saying we know they play soccer. That's the condition. They play soccer. What's the probability they also play AFL? Well, we know that there are 15 people who play soccer. So if we pick someone who plays soccer, there are 15 choices. Of the 15 people in the soccer circle, 4 of them play AFL. So this one's 4 over 15. So now the opposite, the probability they play soccer given that they play AFL. That means we know that they're in the AFL circle. What's the probability they're also in the soccer circle? So the AFL circle, there are 9 choices. Of those 9 choices, 4 play soccer. So the rule for conditional probability of A given B. This is saying we know that B has happened. What's the probability A also happens? So the formula is it's the probability they both happen over the probability that the second one happens. Whichever one is listed second goes on the bottom. We could have used this formula on these 2 conditional questions. So A and S was 4. There are 4 people who play AFL and soccer out of 15 in the soccer circle. So this is a formula you can use for conditional probability. All right, let's go to our last topic of indices. So you need to know 7 index laws. So here are the 7 index laws. So this first one says if you multiply bases, you keep the same base and add the powers. So if you have something like x to the power of 2 times x to the power of 3, x is the base, so we're going to keep the same base and we're going to add the powers. So if you have numbers and letters, do the numbers separately. So something like 4x to the power of 4 times 3x to the power of 7, 4 times 3 is 12, x to the power of 4 times x to the power of 7, keep the same base and add the powers. The second index law says if you divide the bases, you subtract the powers. So if I have something like x to the power of 9 divided by x, Noting that x is the same as x to the power of 1, I keep the same base and subtract the powers. So similarly, if I have different letters and different numbers, I do the numbers separately and the different letters separately. So if I have an expression like this, remembering that this line here means divide, I go 15 over 20, simplifying in my calculator. X to the power of 6 divide x, keep the same base, subtract the power. Y to the power of 3 divide y to the power of 2, keep the same base and subtract the powers. Of course, y and y to the power of 1 are the same thing. So this rule here says, if you raise a power to another power, you keep the same base and multiply the powers. So if I have something like x to the power of 4 to the power of 6, I'm going to keep the same base and multiply the powers. So sometimes you're going to need to simplify an expression that uses multiple index laws. So for an expression like this, I need to use the first 3 index laws. So I'm going to do the brackets first, keep the same base, multiply the powers, times x over x to the power of 8. So now to multiply the bases, I'm going to add the powers, x to the power of 16, divide x to the power of 8. X to the power of 16 divide x to the power of 8, keep the same base and subtract the powers. 16 minus 8 is 8. So the fourth one's a bit different. It says, if a number is not equal to 0, any number other than 0 when raised to the power of 0 is 1. So something like 2 to the power of 0 is 1. 3 to the power of 0 is 1. 4 to the power of 0 is 1. Anything except 0 to the power of 0 is 1. So let's say I had an expression like this. So 3x to the power of 0. I'm raising everything in the brackets to the power of 0. So that will just be 1. This thing here is just 1. And then this one here will be 3 times 1. Here I'm only raising x to the power of 0. Order of operations means do powers first before multiplication. So this will be 1 plus 3 times 1, which is just equal to 4. So this fifth rule says if you have a product raised to a power, raise the first thing to that power, raise the second thing to that power. The power of the product is the product of the powers. So let's add something like minus 4x squared y to the power of 5 to the power of 3. What I have to do is raise everything in these brackets to that power. So I have to raise minus 4 to the power of 3. So whenever you're substituting a negative, use brackets in your calculator. Minus 4 to the power of 3 is minus 64. X squared to the power of 3, keep the same base and multiply the powers. Y to the power of 5 to the power of 3, I keep the same base and I multiply the powers. So in this one, this example here, use this index law and this one. So this one's pretty clear cut as well. If you have a fraction to a power, raise the numerator to that power and the denominator to that power. So let's say I have an expression like this. So I'm going to raise the top, the numerator to that power. So keep the same base. Power to a power, I'm using index law 3 again, keep the same base, multiply the powers. So now I have to raise the bottom to that power. So this index law says I raise 2 to the power of 4, which is 16, and I also raise y cubed to the power of 4. Power to a power, keep the same base, and multiply the powers. I can't simplify any further. I can't say 8 and 12 have a common factor and simplify it because they're powers. This is my final answer and I stop there. So you would have done index laws 1 to 6 in some combination before, but negative powers are probably new to you. So when you have a negative power, you move it to the bottom of the fraction and write it with a positive power. So if I have something like x to the power of minus 5, so I can just write that as 1 over x to the power of 5. I move it to the bottom of the fraction and write it with a positive power. Now, if I have something with heaps of positive and negative powers, anything with a positive power goes on top, negative powers go on the bottom. So let's say I want to write this expression here with only positive indices. So the things with positive powers go on top. So minus 3z goes on top. This 3 here, even though it's a minus 3, it doesn't have a negative power. Z does not have a negative power. Z and z to the power of 1 are the same thing. So positive powers on top, and what goes on the bottom? The negative powers, but I change their powers to positive. So x to the power of positive 4, y to the power of positive 2. The two negative powers went to the bottom, and I changed their powers to positive. Everything else went on top. All right, let's now look at scientific notation. So scientific notation is when we take a really large number or a really small number, we write it as something times 10 to the power of something. So the thing that goes in the first box is always a number between 1 and 10, and the number that goes here is always a power. It's either positive or negative. So how do we actually go about taking a number like this and making it look like this? Well, what you do is locate the decimal point, so at the end, it will be at the end of a whole number. We're going to move this decimal point until the number's between 1 and 10. So if I move the decimal point a few spots, like that, if I move the decimal point here, the number's not between 1 and 10. It's 3,184. I need to keep moving it until the number is between 1 and 10. If I move the decimal point here, the number is between 1 and 10. So I'm just going to write that number. So that's the number that goes in the first box. So what goes in the second box? Well, it's always times 10 to the power of something. The number that goes up here is the number of spots you moved the decimal point. So I moved the decimal point 3, 4, 5, 6 spots. So I put a 6 up here. But hang on a minute. The whole point of writing this number in scientific notation was to make it easier to work with. This number's still pretty long. What we normally do is round to a number of significant figures. So rounding to significant figures is just like rounding to decimal places, except the number before the decimal point, that counts as significant as long as it's not 0. I know that it's a bit confusing. So let's say I wanted to round this number to 2 significant figures. So 3, the number before the decimal point counts as significant because it's not 0. So that's the first significant digit. So I need another significant digit. So if I go to, so this is the first, second, third significant digit. The third significant digit is 5 or more. 5 or more, raise the score. So this is going to be 3.2, okay? We don't do 3.1 because 3.2 is a lot closer to 3.18 than 3.1 is. So this is 2 significant figures, and then I just write my times 10 to the power of 6. This number is pretty much the same as this number, it's just this one's easier to work with. So how do I do scientific notation for a really small number like this? Well, I'm going to do it the same way. I'm going to move the decimal point until the number is between 1 and 10. If I move the decimal point there, it's not between 1 and 10, so I'm going to move it one more spot to here. If I move the decimal point here, the number becomes between 1 and 10. It becomes 9.3. Now to get that number, I moved the decimal point 3, 6, 7, 8 spots. So it's always times 10, and I'm going to put an 8 here because I moved it 8 spots. If the number's really large, if it's more than 1, then the power's positive. But if it's a really small number like this, the power's actually negative. So this number in scientific notation is 9.3 times 10 to the power of minus 8. So because we know about scientific notation and also know our index laws, we can multiply two numbers in scientific notation. This is a number in scientific notation. This is a number in scientific notation. So how would I multiply these two numbers and write the answer in scientific notation? So what I'm going to do is I'm going to multiply these two numbers that are just normal numbers together. So if I multiply 4.4 times 5, I get 22. So now I'm going to multiply the 10s together. So I know from index laws, 10 to the power of 7 times 10 to the power of 9, you keep the same base and you add the powers. 7 plus 9 is 16. So this sum here gives me 22 times 10 to the power of 16. This number is not in scientific notation. The reason it's not in correct scientific notation is this number out the front needs to be between 1 and 10. 22 is not between 1 and 10. So what I can do is I can write 22 as 2.2 times 10. I'm just writing 22 in scientific notation. So I have 2.2 times 10, 22 times 10 to the power of 16. So I leave the 2.2 alone, keep the same base, and add the powers, because of course 10 and 10 to the power of 1 are the same thing. All right, the very last thing we need to do now is surds. So a surd is a square root of a number. If this number being square rooted is not a perfect square, the number is irrational. So for example, square root of 2 is irrational. That means you can't write it as a fraction with integers. That means its decimal goes on forever and there's no pattern to it. Root 2 is like 1.4142 and goes on forever. The square root of say 200 is irrational because 200 is not a perfect square. The square root of 64, however, that is rational because 64 is a perfect square. 64 is 8 squared. Square root of 64 is 8, and whole numbers are always rational. So whole numbers are rational, but if you square root a non-perfect square, it's irrational. So we need to perform operations with surds. So let's look at these two rules here. Root A times root B equals square root of 8b. That means when you're multiplying surds, you just square root the two numbers multiplied together. When you're dividing surds, you just square root the first number divided by the second number. So for example, square root of 6 times square root of 24. I multiply them together. The square root of 6 times 24 is just 144. And the square root of 144 is just 12. Then we're done. As another example, if I have the square root of 30 divided by the square root of 15, that just gives me the square root of 30 divided by 15, which is 2. I can't simplify square root of 2 any further. Square root of 2 is irrational because 2 is not a perfect square. The square root of 144 was rational because 144 is a perfect square. It's 12 squared. So we can use these rules here to simplify surds. So let's say we're just asked to simplify the square root of 80. What that means is I want to write this so it's the same number, but it has a lower number inside the square root. Just like when we simplify fractions, we don't change their value, we just write them with lower possible whole numbers. So what I want to do in order to simplify a surd, I want to find the highest square number, highest perfect square that goes into it. So I want to find the highest perfect square that goes into 80. So the perfect squares, if you didn't know by now, 1, which is 1 squared, 4, which is 2 squared, 9, 16, 25, 36, 49, 64, and so on. They are the perfect squares. So 4 goes into 80. 4 is a perfect square that goes into 80, but it's not the highest. The highest square number that goes into 80 is 16. So using my rule up here, but just in reverse, the square root of 80 is going to be the square root of 16 times the square root of 5, because 16 times 5 equals 80. I chose 16 because 16 is a square number. The square root of 16 is just 4. So, square root of 80 is just 4 times the square root of 5. This is said to be simpler because it's got a lower whole number in the square root. So just like you can't simplify all fractions, you can't simplify a fraction like 7 over 15, you can't simplify all surds. If I wanted to, for example, try and simplify the square root of 30, I can't do that, because the only square number that goes into 30 is 1. It's not divisible by any other square number, so it can't be simplified. Alright, thank you so much for watching this video. Best of luck in your tests, but you're a superstar. You will ace it. This has been the luckiest maths teacher in the world. Have a great day.